Yeah, so I apologize. Anyone who thinks that they're going to get as good a lecture as they heard this morning is in for a disappointment. What I want to do is just give a very simple introduction to periods and from the point of view of regulators. And I'm not going to have, this is material I worked on many years ago, but I haven't spent a lot of time with it in recent years, so I don't have wonderful recent examples, but in some sense that's great because that gives you something to do. But I do have, I think, a good point of view about sort of how to start, how to think about it. And that's what I want to explain. And I should mention that there are notes on my, I don't know my website, but my little corner of the University of Chicago website, Bloch. Website, which make reference to Algebraic lectures. I forget the exact title, but there are 3 or 4 sequences of slides that give more detail than I'm going to be able to give. So if you need more detail, have a look there. So we want to talk about periods, but to start with, we won't take the point of view. Well, let's start with a stupid example. I mean, suppose that we have x, which is, let's say, a Riemann surface, so it's a curve over C. It's a complete curve over C. And suppose we give ourselves 2 points, x naught and x1, distinct points. And then we can look at some path, so call it, say, gamma, which is a map from a unit interval to x, such that gamma of I is x. And if we give ourselves, say, omega, which is a holomorphic 1 form, then we can look at the integral over gamma of omega, and we can say sort of loosely that that's a period. Now, of course, it's not really very interesting because I didn't specify any field of definition for omega. So in fact, I can scale omega by any complex number I want and make my period anything I want. So that's not a very interesting game to play. But we can look at just integration as a functional. So this is an element, if you like, in the dual. As a functional. And it's well defined. It's well defined once I fix gamma, but gamma is not totally determined by the endpoints because I can change gamma by a loop, and so the x0 and x1 determine an element in the quotient x dual modulo the loops, which is just the first homology, and of course everybody knows that this is the Jacobian with J of x. Right? So that was probably familiar, I don't know, in the 19th century. A more modern point of view would be to say, let's try to interpret this integral, this guy, or just the gamma. Let's try to interpret that in terms of an extension of Hodge structures. And there again, the game is quite easy. You write down in terms of homology, you have the homology of x z, and then you have the homology x relative to the 2 points, and then you have h naught. Well, it's just z. More precisely, it's h naught of the 2 points, x naught, x1, but it's the kernel to h naught. Yeah, so it's just one copy of z. And you notice that this is an extension. An extension of pure Hodge structures with weights 0, which is this one, and here weight -1. Right? And I assume that you've encountered Hodge structures, and if you think about mixed Hodge structure, you realize that the extension class is determined by gamma, right? Because gamma is the path from x0 to x1, so it represents a class in h1 of x, x0, x1. So it determines a splitting, a rational splitting. It's a z class, I should say, which splits this map. So it determines a rational splitting, and I won't go through the whole song and dance, but from that rational splitting, you find a representation, an element, a certain kind of an element that determines the extension of Hodge structures, and so you find that this gamma essentially gives you an extension. Hodge structures. So that's a very important theme, and I want to emphasize that. We're not actually taking the interval, we're not actually computing the period, but we're focusing on, so to speak, half the period, namely the chain, and we're arguing that that chain determines an extension of Hodge structures, and that extension of Hodge structures contains the essential interesting information. Okay, and I want to hammer that home with a couple of sort of increasingly complicated examples. In some sense, everybody knows about Jacobians curves, and everybody knows, or most people certainly know, about Griffith's theory of intermediate. Jacobians. It's the same thing. What do I mean by that? I give myself my x, but now instead of just 2 points, so x will now be a smooth, let's say, projective variety. And I'll give myself a cycle, so z is some n zi is a codimension p algebraic cycle. And I'll assume that z, the class of z, it represents a cohomology class in H2P of x with z of p coefficients. Always in this story, there's a certain ambiguity about torsion. I mean, sometimes one's tempted to tensor with Q, but let's don't worry about that. And suppose that this class is 0. And of course, in the case here, so the example is simply the x1 minus x0, which is a 0-dimensional cycle will be homologous to 0. So we assume that the cohomology class is 0. So then we can write down directly this extension of Hausdorff. And it goes like this. If we look at H2P minus 1 of x z of p, and then we go to H2P minus 1 of x minus the support of z. So I write support of z. So the support of z is simply the union of z i's. And then the Giesen sequence, or whatever it's called, will say that the next term in the long exact sequence is basically going to be the sum over the index set of the components of a copy of z, one for each component. And then the next term will go to H2P of x z. And by purity, I find that I get 0 here. And my cycle class, remember I have not only the components, but I have certain multiplicities, and put all together, I assume I get something homologous to 0. So the multiplicities determined for me a map like this. So this is the ni's. And this map is 0. And so if you do a little bit of homological algebra, you find you can pull back and you get a certain extension called E with the same H2 minus 1 x z of p goes to 0. So in other words, cycles homologous to 0 give me elements, give me extension classes. So my z, they give me an element in X1 in the category of mixed Hodge structures of z. This is z of 0. I should stress as Hodge structures, they're just absolutely the trivial Hodge structure of z of 0 by what comes here, H2P minus 1 of x z of p. And this is, of course, the Griffiths intermediate Jacobian, JP. It's isomorphic as a torus. Let's see if I can get this right. It's H2P minus 1 of x c modulo f. It's cleverer to put the twist of p in here because that changes the Hodge structure. And so now I can write f0 H2P minus 1 x plus H2P minus 1 x z. So if you look back at the Jacobian game, what I've done is I've written this as H1 x c H upper 1 xc, maybe I want c of 1, modulo f0 h1 x c of 1 plus h1 x z of 1. And that, I didn't do the calculation, but if you write it down carefully, you find that you were exactly, that this coset space is exactly the isomorphism classes of extensions. So similarly here, we get this intermediate Jacobian, and we get these isomorphism classes. And to bring it back to periods, when you look at what you're doing here, what you're doing is essentially computing integrals over a certain chain, and I'll call it capital gamma, such that the boundary of capital gamma is 0. By assumption, z is homologous to 0, so I can write down capital gamma, and you'll find that, just vaguely speaking, that the whole process here is controlled by the integral over capital G. That's familiar. So that's two familiar, or presumably for the most part familiar examples. Let me do a third example along the same line, which I find is maybe a little less familiar. And I would love if people would look carefully at this kind of thing. And in fact, before I start, let me just say I think people are. I think this arises in the theory of automorphic forms. For example, something called Kudla's conjectures, or conjecture. I'm not an expert on such things, so, oh dear. Now we have to wash the car, sorry. Anyway, let's write down a third example of this game, where periods are playing a role, but in a sort of a different way, not the same as the familiar number. Okay. Now I got to dry the car. So for the next example, let's just give ourselves, say, f from x to y, a map of varieties. So suppose that x and y are smooth projective varieties. And in that kind of picture, we can write down a long exact sequence of cohomology for the relative. I mean, it's sort of a relative situation. So we can write, let's see, how does it go? H, I guess n minus 1 of y goes by f over star h n minus 1 of x goes to sort of hn, I don't know how to write it, I'll just write y relative to x. That would be the notation if x was a subvariety of y, but I don't need to assume that. And then we go to hn of y. X. Now, I neglected to point out, unfortunately it's still on the board there, a crucial feature of the kind of extensions that we are getting, namely that the weights, so let me write down, so up there, go back to the previous example briefly. So up there we had z, and it corresponded to an extension that looked like h2p minus 1, x z p, and then there was the fellow in the middle, which I'll just label with a z because it depends on z, and then we had the z of 0 goes to 0, And the point that I want to make is that this fellow is pure of weight 0 as a Hodge structure, and this fellow is pure weight -1, right? Because twisting by 1 has weight -2. So twisting by p has weight -2p. On the other hand, the cohomology in degree 2p -1 has weight 2p -1, so altogether we get weight -1. So the kind of extensions that we're used to working with algebraic cycles in this way have sort of a difference of weights. On the left, it's 1 less than the right. Okay? Well, look at what happens here. I assume that x and y are smooth and projective, so this fellow has weight n-1, and by the same token, this fellow has weight n. Right? So what we're going to do, using the fact that Hodge structures, or I could be talking L-adically, or these form an abelian category, so I can take kernels and co-kernels, and I can cook up an extension where the difference of weights is exactly the 1. So let's do it. I guess I have h n-1 x modulo the image of f star, and then that goes to the fellow in the middle here, and then that goes to the kernel of f star goes to 0. Okay, and this has weight n-1, and this has weight n. So we can ask ourselves, well, is this extension, which clearly is motivic, does this have anything to do with algebraic cycles? And you see, one thing you can rule out right away is anything like an intermediate Jacobian, because this situation a priori is completely rigid. There's no possibility of something being homologous to nothing. There's no homologous to 0 algebraic cycle that stands out in this picture. Right? So, but don't give up.
You are a little bit.
Say again?
So this is a little bit strange here, because you said I have a map x to y, and then you wanted to introduce h and y, x. And then you said, okay, I can assume that this is an inversion.
No, you didn't.
No, I don't care. I said if it was an inversion, then you would have seen it before.
Define it, or
No, I didn't define it, but I'm sure that there are in the audience great experts on
Exactly. I think so. That's the commodity of the coin, no?
It's a cone. It's a cone. Yeah, it's a cone. And really, at this point, we're not doing anything tricky, right? We're just talking about the cohomology of topological space.
Yes, exactly.
And a little bit more because I want to claim this as a Hodge structure, because we're talking Hodge structures. But there's no problem. I thought you were going to say, what I thought you were going to say is, where did n come from? Right? Because there's no n. I mean, the crucial data is just a map between varieties. And why should I pick an n? And that's the crucial observation. I shouldn't pick an n. So what I should do is this. Let me explain how to think about this. I don't have to remember how this goes. So if I look at x cross x, then I can look at x cross y, and I can look at y cross y. And so here I have the diagonal on x, and here I have the diagonal on y. And those are algebraic cycles. Can't argue with that. And here I have the graph of f, which is also an algebraic cycle. And let's see, how does it go? X maps to y, so I have here identity on x cross f, and I have here the identity, or F cross the identity on Y. Right? And what I find is that gamma F is actually physically equal to, but I mean in particular in terms of the calculus of cycles, it is F, it's the identity cross F lower star of the diagonal on X, but it's also equal to the other one, F cross identity on Y, upper star of the diagonal on Y. Right? Now, that's my cycle. That's going to play the role of the Z. So this, all this data here is Z. And there's no n here. So what I'm going to do is I'm going to get all the n's at a blow. I'm going to get an extension that encapsulates all the extensions n. And how does it go? We gotta watch the car again. So what I can do, let's see, if I look at the cohomology of, put it about here, if I look at the cohomology, in some degree, we'll maybe specify it if anyone is interested, of X cross, let me get it right here, yeah, X cross X, and the cohomology in some other degree, I don't know, maybe call it double star, of Y cross Y, then by a push forward and pull back, I get a map here, identity X, F, no, identity X, F, lower star plus F cross identity Y. Upper star, if I've done it right, I should end up in the cohomology in some degree of, I guess it's degree double star, of X cross Y. And let's suppose I need to give some twists to make this look realistic. So suppose that D is the dimension.
What happened to star? Can you call the left stars I and J? Because the other star has different.
Yeah, let me be more precise. Okay. So I'll give some numbers here. Stars are ugly. So
yeah, but some stars are induced maps of.
right. So we're gonna fix all that. It's gonna be great. We'll see. So we'll write E for dimension of Y, and here I'm going to want 2D and a D twist, where D is the dimension of X, and here I'm going to write 2E and twist by E, so that in here I have the class of the diagonal of X, and in here I have the cohomology class of the diagonal of Y, And then this is going to go to, I guess, 2e, right? 2e, yes, twist by e. And in there, I'm going to have the cohomology class of the graph. F. And so what happens is that these two classes both map to here. Okay? So if I take the difference, then that goes to 0. Because they both map physically to the same plot. Well, okay, so what I can do is to write down a long exact, I can relativize this. I can write down as a relative term. You can always do that. And then the previous term is going to be this cohomology, but in degree 1. So I'm going to get h2e minus 1 of x cross y twisted by e. But I want to cut it off there, and so I'll factor out by some relations that come from the, I have a long exact sequence of Hodge structures, and I'll just cut it off. And similarly, I'll cut it off here by taking some sub-Hodge structure and put a 0 there and end it. No, sorry. I went too fast. That's not what I want. Sorry. I want to go one step further. No, this is cool. This is good. Yeah, this is good. Because what do I have here? I have exactly the same situation that we had when we looked at the intermediate Jacobian. Namely, I have a cycle that goes to 0. Right? And so I've got a map from z of 0 into there. And it goes to 0 here. And so I've cooked up an extension, an element in x1 of h2e, z of 0 by h2e minus 1 of x cross y twisted by e. And notice this has weight, this again gives me minus 2e plus 2e minus 1, so this has weight minus 1. So indeed, I'm in the same Hodge realm that I was before. I have an extension of relative weight minus 1. And so what happened historically is there's no intermediate Jacobian, right? I mean, I started out with something that's extremely familiar. I started out with a map between algebraic varieties. That's all that was where we started from. And lo and behold, we get this X class, right? But nobody seemed to work on this, but it seems to have come up, and here I really go out on a limb because I don't know what I'm talking about. But the automorphic forms people, in particular Kudla, they've been working with pairs of Shimura varieties. So they have one Shimura variety mapping to another Shimura variety. And somehow they end up in exactly this situation, where they get an extension class, but they don't really understand it from the point of view of algebraic science. But it is just exactly what I've done here, but done in the context of automorphic. I open the floor to ideas about how to write down interesting such classes. And let me tell you again vaguely, because again I don't really know the theory, but what would you do if somebody gave you, for Christmas, a class like this? What would you do with it, right? Well, what you do with it is you compute, well, actually with it alone you might have a little trouble, but yeah, no, you compute the height parent. So maybe I say a word about height pairings. So actually, let me just see here. I don't want to run on too long. I started at 2:30. Okay, so I owe you, let me just tantalize you a little bit by saying the word height pairings. Because they come really logically after another discussion. So I propose to give another discussion, and then if we have time, we'll get to the height pairings. The height pairings, you see, the problem is, when you say period, you like to think of a period as a number, right? But our numbers, what we've constructed so far, are elements in compact Lie algebras, I mean Lie groups, namely toruses, compact toruses. But a point in a compact torus is not really a number. Right? It's a number up to the periods, but the periods, they mean that you really don't get a number out of it. But heights give you a way to win and get numbers, even when you start out with things that are numbers. Seems strange, but there it is. Okay, but that's hopefully in a half an hour. Let me go on logically with the story.
Can I ask you a question on arrays? So does the decomposition theorem say anything sensible about the extension class in your third example?
The decomposition theorem.
For example,
What would
if your
it
map
say?
is smooth, then I assume that the extension class would be 0 or something like that.
I doubt it. I don't think so.
Because then
It's
the
not really simple, so it's.
So what's the logic? Why
well,
is it?
I imagine that this cohomology hn of y comma x, that's you take the map from the constant sheaf of y to the the right push forward
Yes,
and take the corner.
yes,
Fine.
that's fine. Yeah. Mhm.
But doesn't
No, but you
in the what
you
the
get
link
something.
proved in this that if you have a smooth map, then this map actually splits.
Oh, if the map is smooth.
If the map is
If the map is smooth, yeah, then that's a whole different kettle of fish. But I don't want to assume the map is smooth. I want to assume that x and y are smooth.
Yeah, but if it's non-smooth, then you have the decomposition theorem and like.
Yes, you have a decomposition theorem, which would be an excellent tool to try to understand, but it wouldn't say the thing is zero.
Yeah, I'm not saying that.
No, you're absolutely right. That would be the way to start out to try to understand.
In the decomposition theorem, we work with intersection cohomology or something like this, and this is not intersection cohomology.
Well, but everything is compact here. So, yeah, maybe, yeah, right.
Something.
No, you're right. I mean, I've not thought about it. Let me shut up because I have not thought about it that way. It's a great idea. One should think about it that way.
I think that would work, because the intersection cohomology groups of these minimal push forwards, these minimal extensions of local systems carry Hodge structures themselves.
Right.
That's exactly what you
No, that would describe the extension, but it wouldn't say the extension is zero. Now I've lost the thread here. Let's see. So what am I doing? Oh yeah. So let's change the subject a little bit and try to get some numbers. So one way to get numbers is to replace our smooth projective variety by a product of a smooth projective variety with an affine space. So there are two ways to do it. You can do it either simplicity or cubically. I'll just, for purposes of discussion, I'll say it doesn't matter. I'll say cubically. Box n, where box is P1 minus 1, and box n is box plus box n times. Okay, so we go back to our algebraic cycle game, and we look at algebraic cycles on here. So we take z, summation ni zi is the codimension P algebraic cycle on X cross box N. Right? And we want to impose, I don't want to get too much into detail here, but we have various faces obtained by setting the parameters. So box has a sort of standard parameter t, and it contains the points t equals 0 and t equals infinity. And if we take box n, of course we have n parameters, but each of them can be set equal to 0 or infinity. So we get in that way various sort of cubical face maps embedding this in here. And we want to do basically simplicial algebra. Unfortunately, for other reasons, we've chosen a cube, so you have to be a little bit careful doing simplicial algebra with cubes, but it's understood. That's an understood problem. So in particular, we can look at all the various face maps. Do it like this. And we can look for cycles which are represent classes in the sort of the co-simplicial in the sort of co-simplicial, well, it's a co-simplicial scheme, but then the cycles are contravariant, and we assume they meet the faces properly, so we can pull them back and get a contravariant object. And in that way, we can write down sort of, well, what I don't want to get too much into it, but we can sort of write down the Chow group of codimension P of X cross box N, but relative to X cross box N minus 1. Or, no, better, no, it's not what I'm saying, X cross the boundary of box N. So we look at cycles that meet sort of all the faces trivially, something of that sort. So there is a calculus of these things. I don't want to spend a lot of time. It's familiar now. It goes back to actually McLean, I guess, in the 1930s. But in any case, these carry cohomology classes. So if I have a Z, which represents a class in here, then I can talk about the cohomology of Z in H2P of X cross, but now I'm doing topology. I'm looking at Betty, say Betty cohomology or something like that. So this box, relative boundary of box, is just a sphere. Right? It's an n-dimensional sphere, so here I can just write Sn. This. But it's familiar that if I take the cohomology of something crossed with an n sphere, that simply subtracts n from the cohomology of X. So this is isomorphic to H2P minus n of Xp. So we now notice that we've done something extremely stupid. because the Hodge structure is going to tell us that the class of an algebraic cycle is a Hodge class. Right? But if n is at least 1, there are no Hodge classes. So up to torsion, which we've agreed to ignore, this class is going to be 0. So in fact, this is going to be 0 for reasons of Hodge structure. Okay, but that's not the end of the story, because we actually started our day with looking at the cycle x1 minus x0, and certainly that, the cohomology class represented by that cycle is 0, and that made us very happy, right? Because that enabled us to define a class in the Jacobian, which was much more interesting than homology in this case anyway. So similarly here, we can define, for such a z, we can define a class in an appropriate Jacobian. So we get a class of z, which is in, how to say it, so let me write it first, in the Jacobian of this h associated to this h2p minus n of x p, and actually there should be a minus 1 here, because remember that, so we should have a minus 1, and so what am I trying to say here? Well, when you work this out here, what you get is that this is isomorphic to h2p minus n minus 1 of x c of p modulo f0 h2p minus n minus 1 x cp plus h2p minus n minus 1 x z. So this is again the same idea that we'd like to calculate extensions of Hodge structure in this degree. But notice something nice has happened here. Whereas before we had a compact torus, right? Before the Hodge piece was, so to speak, half of this real vector space. And so this then was a lattice of full rank in the quotient. But now it's not. And I think it's maybe better to look at an example here just to get a sense of how the game is played. So we're going to be able to get numbers from this machine. And by the same token, those numbers are periods. But then I want in the remaining time to at least vaguely explain the Beilinson conjectures and what those periods are supposed to have to do with the first non-vanishing term of Taylor series expansions at integer value points of alpha. Unfortunately, time has been a little tight, but I do want to just do one example here, two examples. Let's look at, because I mean, what happens when you get these indices, it's very difficult to follow what's going on. So let's look at some example. So suppose I take x to be, well, why don't I take x to be a point? So if x is a point, actually I didn't think about what happens if x is a point. Let's see. We're looking, we want to look at chow p just of affine space in dimension n, but relative to the boundary. And that should carry a class, and let's see if we can do it here now, which should be an extension z0. So let's notice, even though x is completely stupid, once I take affine space and I start looking at cycles on it, I got lots of stuff. And it's easy to see, even when n is 1, it's easy to see this is not trivial. So we have some extension which depends on the cycle. And what comes here is, well, what's the cohomology of a point? Well, it's just H0. And we have to keep track of the p twist, so in fact it's going to be z. P, is that right? ZP? I hope it's ZP. But to get these extensions, I have to take, I'm going to want to take, when we work it out, n is going to want to equal to 2p minus 1. Since time is tight, I'm not going to do the calculation here, but if you look, if n is 2p minus 1, then I'm going to get n plus 1 is 2p, and I have 2p minus 2p, so I get h0 up there. So the extension, the x, when we calculate mixed Hodge structures of z of 0 by z of p, is h0 of spec q. C p modulo. There's no, the Hodge filtration piece vanishes, and so I'm simply left with z. So, such classes can exist, and they do exist, and that's a very simple example. It's over here, you can correct me if I'm wrong, but I think that the interesting example would be Z codimension 3 class in box 5.
So,
Mm-hmm.
if you have an extension of Z0 by ZP, doesn't that mean something like a p follow
Yeah, so you were asking what is the extension class? Yeah.
But no, I mean the extension class is given by p follow.
Yeah, so
one should be the follow.
that's right. So for example, since I said spec Q, we expect interesting classes corresponding to odd values zeta 3, zeta 5, and so forth, and that means P should be 3, 5, and so forth. But be careful, because P being 3, 5, and so forth, when n is 2p minus 1, it gets more complicated. So the cycles, the dimension of the cycles is slightly trickier, right? Because n is 2p minus 1, so for example, for zeta of 3, I want 2 times 3 minus 1, which is 5. Right. And so, okay. Yeah. One more quick example, and then I want to finish by stating the Beilinson conjectures. So another quick example, let's suppose that x is a curve, And suppose we want to look at chow 2 of x cross box 2. Box 2 relative to box 2. So this is related to the K2 and Milner symbols. Namely, if I have two, say, f and g functions, q of x, metamorphic functions, then I can look at the double graph called gamma of f and g, and I can view that as being a certain cycle on x cross box 2. I mean, roughly speaking, it's the collection of all x, f of x, g. Time is tight, so I'm not going to be more precise. And then you can take linear combinations of these gamma fi gi, and you can cook up elements in here. And then you find, in terms of your Hodge extension, that this is going to buy for you an extension of H1 x q of, q of 2, I guess. Q of 2 goes to E, goes to Q. I'm shifted from Z to Q. A torsion is an ongoing issue here, and sometimes it's better just to ignore it. Tensor to Q. You get extensions like that. Okay.
Sorry, there's some condition.
Say
Is
again?
there a condition on the sum mi gamma fi g?
Yes, yes. There's a complicated condition.
So the usual tame.
The tame symbol, yeah. So there's a not every such. I mean, that's the general theme with these things. You see, when I write the Chow group relative to the boundary, that's a condition which I haven't explicited, but it's a very subtle condition. I mean, the cycle can meet the boundary, but you better have another component that meets it with the opposite multiplicity, and it's a whole complicated song and dance. But anyway, just to finish the lecture, I want to explain why anyone cares about these things, and what the numbers mean. And the numbers, the meaning is explained by the Beilinson conjectures.
Before you do that, you said something about heights.
Yes.
So this.
Yeah. So okay. Yeah. So let me say a word. Let me write down Beilinson conjectures. And there are 3 cases. And the reason why most lectures trying to explain the Beilinson conjectures end up in a train wreck is because the lecturer tries to explain all 3 cases. Okay? I've been on this train track once too often. I'm not going to try to explain, but let me just say there are 2 integers that come into play here. There's the n, which is the size of the box, and there's the p, which is the codimension of the cycle. Right? And the controlling number is 2p, well, it's better written as n minus 2p. And if n minus 2p, we want this, well, as a first approximation, we want it to be less than or equal to, sorry, the other way around, we want it to be less than or equal to 0. N minus 2p, sorry. Yes. No, but I should. the cycle case, sorry, this is very confusing. Let's just look at n. N is the size of the box. There are three cases. The case n equals 0 when there's no box. That means we're just talking about cycles on X. The case n equals 1 when the box is just a one-dimensional box. And the case when n is greater than or equal to 2. I'm going to focus on the case where n is greater than or equal to 2, just so that we get out of here in finite time.
So is n the K group, the
N,
degree of the K group?
so when n equals 0, we're talking about just algebraic cycles.
Yeah,
Right? When n equals 1, we're talking about K1.
yeah.
Here, the statement of the Beilinson conjecture, so here is where the heights come.
Mm.
Okay? Here, the statement of the Beilinson conjecture is still somewhat tricky in the sense that there are two pieces of the relevant. And here, it's a pure statement, and I can make it in 5 or 10 minutes. Okay, so let me focus on this case. So we want to look at the, let me see, I wrote down the numbers here. We want to look at, let's write down our intermediate Jacobian. I gotta wash the car. Sorry. So we're looking at cycles of codimension P on X cross box N, box N. And these, the extension class lives in, so the class, so Z, let's say, is in here. So I'll use some tricky bracket for Z to indicate the class in the intermediate Jacobian, which in this case is H2P minus N minus 1 of X CP modulo is F0 plus H2 minus N minus 1 Z of P. And there's a very important thing which years ago I didn't understand correctly, and that was one of the really the great insights that Beilinson had, even though it seems in retrospect rather simple, was that one needs to look at the real Frobenius, the real conjugation, and take the plus part.
Sorry, Spencer, do you mean you mean F0 of the whole cohomology plus the integral part?
Yes, F0 of, yes, rather, rather F0 of this plus this. Okay. Now, this is a sort of abelian Lie group for the range of indices that we care about. And let me rewrite it slightly differently. I wouldn't assume that X is over Q. And so then if I forget about the discrete part here and just look at this part, I can express it in terms of algebraic de Rham cohomology of X over Q. So I can write this as H belong x over q in degree 2 p minus n minus 1 modulo with a p twist. So p twist in this context simply means I shift the Hodge filtration by p, and then I take f0 of this thing here. And this is a Q vector space, so it has a Q structure. Right? So I can look at the determinant of this Q structure, and I can fix an isomorphism with Q. So I'll choose it. And if I chose a different one, I would introduce an ambiguity, but that ambiguity would simply be a non-zero rational number. And the Beilinson conjectures only work up to non-zero rational numbers. So I really don't lose anything by choosing such a thing. But I gain this determines a volume on, let's give this a name. So we'll call this J. It's, as I say, an abelian Lie group. And by fixing this element in the highest exterior power of the tangent space, so this piece here is the tangent space, I mean, without the discrete part, then I fix a volume. So this quotient here, it turns out, is discrete, but it's not a maximal lattice. Right? However, Beilinson conjectures, what did we do? We showed that to an element in our Chow group, we can associate an element. Now, if we imagine our Chow group as being a lattice, that's going to give us a collection of elements in here. And if we are really lucky, that collection spans a sublattice, or a discrete subgroup of our abelian Lie group. And if we're really, really lucky, the quotient by that discrete subgroup is actually compact. And so Beilinson conjectures that if we look at this, our J here, which is the stress, we have to take the invariance under the real conjugation. If we take J and we factor out by the image of the cycle map, which associates to each cycle its extension class, that this should be compact. And so we should be able to compute, and we have a measure. We have a volume. So we compute the volume, or the co-volume of this lattice. So the volume, let me say, of J modulo this image of the cycle. And the Beilinson conjectures hang on two ideas. First of all, he says that the rank of this Chow group, and let me use his notation now because it's really much better, he writes this as H motivic. The index here is 2p minus n, 2p minus n, x, and then h2p minus n, x, and then p. So the rank of h to p minus n of x p, well, I don't have to say that. He conjectures that, well, that this is equal to the real dimension of J, let me write JR, where I factor out by the real. So it's in general, when you have an abelian Lie group, you can sort of take the maximal factor out by the real span of the lattice and get a vector quotient called JR.
So J is the Frobenius invariant part. and
J is the plus part, yes. J
Yeah.
is the,
You're missing a subscript M
I'm missing the subscript.
on the typical energy.
Yes, yes. Well, here I have P and two P
Yeah, but
minus
it's
N.
typical module, you want a subscript M.
Oh, yes. I thought, my God, I've got a 3 minutes. Yeah, so this should be, just to finish up, this should be the dimension here. And what's more, the volume of the quotient. So the volume of J modulo the image of this H 2P minus M should be equal to the first non-vanishing Taylor coefficient in the expansion, the Taylor expansion of the Hausdorff L function. I'm sorry, it's kind of late in the day to introduce Hausdorff L functions, but we associate it to each of the cohomology groups, L-adic cohomology groups. We can define a Hausdorff L function, and just let me get the right twist here. It's the same. It's the 2p. It's this one. H2p 2p minus n minus 1, but L-adic now of x bar s at where, and I hope I wrote it down because it's always difficult to do that calculation, at s equals p minus n. And just as a reality check, if we went to the case of the curve, for example, remember we were looking at cycles associated to pairs of functions on the curve, we would then, so to these gamma fg, we would then get classes in H2 motivic of the curve with the 2 twist, and that would be related to the L function of H1 of the curve, the L-adic Q bar, L-adic, at the point s equals 0. I think I probably should stop because everybody's tired. There's, of course, infinitely more to be said, but that's at least the first dose, and I leave it to you to sort out. I haven't emphasized the role of periods, but you sort it out and you find, indeed, that these numbers are periods. Okay, so next time.
When rank is equal, you mean up to a rational multiple?
Yeah, sorry, absolutely right. It's lightly down, as I said. Equals up to 2.
And you say that this volume is a period in a natural way.
No, I didn't say that. I said the individual elements. I mean, it's a determinant of periods. I don't know, is it a determinant of period or period? I guess, yeah. I mean, it's a ring, so, yeah. But the word, when you said natural way, I kind of shied away. No, this is confusing because the theory becomes considerably easier when there's only one element. When the thing vanishes to order 1, then there's one element, and somehow the theory is much more elementary.
So it's not clear, but determinant is the same as this volume, right? This is the way to interpret it.
Well, so that when I have a Q vector space, a finite dimension, I take as determinant, that's a one-dimensional Q vector space. If I fix an element in that one-dimensional Q vector space, that fixes a volume on the original Q vector space. Right? And that's what I'm saying.